So, I will start with this famous quote by somebody called R.T. Rockefeller. Who has done amazing amount of work on convex analysis and variational inequalities. He has a very nice book on convex analysis, this R.T. Rockefeller. So, if you get a chance, try to read about this. Okay, this is very, very good. And he mentions that the great divide, okay, so there is a big disparity not between linear and nonlinear, but it is in fact, even bigger gap is between being convex and non-convex, okay. Optimization is all about exploiting convexity, and as soon as you hit non-convexity of some type, it creates lot of issues, okay. So, the subject of this half an hour session is detecting convexity automatically, okay. So, if you are able to write a model, then as a modeler you should be able to say whether your model is convex or not, okay. Because if it is convex, then you can just give it to a local solver, okay, who does not have to do factorable functions or create linear relaxations, then do branch and bound on those, and you do bound tightening, cutting planes, heuristics, and so on and so forth. Okay. Life in the convex world is amazingly simple, okay, thanks to nice properties of convex functions and convex sets. Okay. So, if you are writing programs or writing models, writing a convex model is very, very useful, okay, if you want to solve it. Okay. On the other hand, if you are solving, or if you have you are in the business of accepting problems and trying to solve them, then you should have some method of saying whether what the user has given to you is actually convex or not, okay, because if it is convex, then you can exploit lot of properties. Okay. So how do you detect convexity? Okay. So so some of the rules are very simple and we know already. Okay. So what are the properties of convex functions which we can already exploit to say that, to check whether some given function is convex or not. Okay. So what is one such property? What is positive semi-definite? Hessian. So f is convex, okay, f is convex if and only if Hessian of f is positive semi-definite where on 1x or boundary points on all x, right, at every x in domain of f, okay. All right. Is this an easy property to check? Can you check positive semi-definiteness of a matrix? Yes. How do you check that? So, you compute the eigenvalues of that matrix, or do some factorization, like what? Cholesky, right. So you do some decomposition and it will give you an idea of whether its eigenvalues are positive or negative or not, right. So that type of analysis is possible for the case when this Hessian is constant everywhere, okay. For example, for quadratic functions, okay. If the function is not quadratic, then this Hessian keeps changing depending on where we are, depending on x. So that means you may have to evaluate these eigenvalues or do this factorization at all possible x's, which is not really possible, okay. So we need more tests or more checks on what is convex and what is not. Okay. So, so let's start, since we are talking about quadratic functions. So let's say, let's look at the case of, so suppose f is of this form, okay, C transpose x plus half x transpose qx. If I look at the Hessian, this would be your Q matrix, okay, and if it turns out to be positive semi-definite, then we are fine, okay, we are, function f is convex, okay. So this works very well for quadratic functions. Only thing is that it may not always be a great idea to evaluate eigenvalues of Q when it is very big, okay, when f has too many variables, or Q is dense, or very large, okay. But that is still okay as compared to the time it may take to solve it to global optimality if Q is not positive semi-definite. So sometimes it is worth investing that much computational effort if it saves your life later on, okay. So let's look at one variant of this, where even when Q is not positive semi-definite, we might still be able to say things are easy and convex, okay. So let's look at an example, very simple example of minimizing a straightforward quadratic function. Minimize, let's say 101 x1 square plus 101 x2 square minus x3 square, subject to let's say x1 plus x2 minus x3 equal to 1, okay. Now this is a QP, or a quadratic optimization model, and if you were to decide which solver to use, you may just look at the quadratic function in the model and say that this is non-convex, okay, because the Hessian has a -1 on the diagonal, okay. But a simple trick of reformulating this, okay, so I can say that x3 is actually equal to what? x1 plus x2 minus 1, and substitute it here, okay. What will I get? Okay, so this model, remember we talked about reformulation, so this model is exactly same as 101 x1 square plus minus x1 plus x2 minus 1 whole square, and if you open it and expand it and write the new Hessian, it will come out to be positive semi-definite, okay. So even though the function may be non-convex to begin with, after some reformulating ideas, it may turn out to be a convex problem after all, okay. So you may instead want to solve this, which will be far more easy to solve, okay, rather than searching globally for some solution, okay. You can generalize this idea, instead of having such a simple example, we can just say that suppose my quadratic function is half x transpose qx, subject to ax equal to b, okay, and no inequalities, no bounds. I can substitute, if Q is positive semi-definite, then I am already sure that this is an easy problem to solve. But if Q is not positive semi-definite, I may be able to substitute out some variables into these x's, and then get a reduced Hessian to check, okay. So if that turns out to be positive semi-definite, we are still okay, okay. So this is one trick of avoiding to solve problems as non-convex optimization problems, alright. Let's look at few more ideas, okay. So I'll start with a question, okay. So this quadratic case makes sense, alright. Let's see, using your intuition or whatever ideas of convexity we have read about so far, can you tell me which of these functions is convex and which is not, okay. So first function is x minus 1 whole square, okay. X minus 1 whole square plus 1 whole square and x minus 1 whole square minus 1 whole square, alright. Very simple, 3 functions in one variable, okay. You can even plot it and check, but just using your basic intuition, which of these functions are actually convex and which are not. What about the first one? Convex, looks like a convex function, okay. Is there some easy argument to say why it is convex? It is some even power of a linear function, okay, or an affine function, so this might be convex, okay. What about this one? Convex, alright, convex. What about this one? Mustafa? Convex, alright. So all of you think these are convex. It turns out that the last one is actually not convex, okay. So this is not convex, these two are in fact convex, okay. And you know, when you go back home you can try to plot and see why it is so, okay. So one rule which we can use for you know these type of things is the following, alright. So this property is quite useful. So I'll write this property, okay. F of g of x is convex if f is convex G is convex and what, anybody? G is F is increasing, okay. So what I have written is that non-decreasing, yeah, so that is good, okay. And F is non-decreasing. Okay, so do any of these satisfy these conditions? So what is F in these case, in you know, for example in this case, middle case or the third case, what is the function F? Square, okay. And what is the function G? It is this x1 x minus 1 whole square plus 1 or x minus 1 whole square minus 1, right. So are these increasing functions? Not really, these are quadratic functions which go down and then come back up, okay. So in fact if you plot this function it will come out with this shape, okay. Because this part actually becomes negative for values of x near 1, okay, and then it will turn up because square of negative is again positive, okay. So, this rule is somewhat useful, but this is not an if and only if condition. So, if this rule is violated, things may still be convex, okay. So, for example, this particular function violates or does not satisfy both all the requirements, but still it is convex, okay. So, so in fact there is no no algorithm that you can follow step by step and say that a given function is convex, okay. You have to apply a bag of tricks to say that if this property holds, or if that property holds, or if some other property holds, then that is function is convex. Similarly, there are a bag of tricks available which say that the function is not convex. So, you can try this property, that property, something else, and say that this function is actually not convex, okay. But there is no sure shot definite algorithm which says that given function, I will be able to find out using this algorithm whether this function is convex or not, alright. So, detecting convexity is more or less like a hit and trial or following a few set of rules and then moving on, alright. The local nonlinear optimization solvers like IPOpt or Minos or SNOpt, K-nitro, they do not even bother checking for convexity of a given problem. They just assume that some nonlinear functions are given and you would like to find the minimum, local minimum or something. On the other hand, solvers which want to solve to global optimality, they would really like to exploit convexity a lot, and they tend to spend some time in checking whether what the user has given as input is actually convex or not, okay. So they would try these bags of tricks, bag full of tricks to say whether this function is actually convex or not convex, okay. Why is this definition true? What is the proof of it? Most likely you may have to apply, I am just guessing, I did not read the proof, but most likely you apply the chain rule and see whether the positive semi-definiteness property of second order derivative exists or not. Talk to Mustafa, okay, he knows the proof, alright. Or so any other questions? Okay. Similarly, a similar rule is f of g of x is convex if f is convex and G is concave, okay, G is concave and G non-increasing, G non-increasing in its domain, okay. So this also is in fact I think G, okay, not F, so we can check, okay. So in both cases G, it is the monotonicity of G which is important, okay. Okay, so I may be wrong, but we can double check, okay. So this is also quite useful because many times you may want to check for concavity also, because later on there might be a negative of that concave function, okay. So which will become convex, alright. So, both these rules are quite important, but they are not sufficient to always check for convexity. Okay. There are also many other simpler rules that we already know of. So, for example, linear functions are both convex and concave. Negative of a convex function is a concave function, negative of a concave is convex. Sum of convex functions is convex. If you multiply by a positive number, a convex function remains convex. If you multiply by a negative, convex becomes concave. Okay, so these are very simple rules, but these can be stitched together to check for some checks for convexity of more complicated functions. Okay, so you can do term by term convexity check, for example, and say that this is a convex function. Okay. Let's see some other functions and see if we can tell what about them. Okay, so this is a very common function, x1 square plus x2 square plus some constant k, where k is greater than 0. Okay, what about this function? Convex. Okay, used in distances and such. Okay, but again, difficult to apply these rules and say that this we know already from some other analysis that these are convex. Okay. What about this function? This is a convex function. Why? Or where do we see this? No, this is a product, x times log x. So this is not a composition of two functions. Okay, this is a product of two functions, and usually product means a bilinear term which is not really convex, but so this is also called a negative entropy function, and you can plot it, for example, to see whether it is convex or not. Okay. What about this related function to entropy? F of this is a function in two variables, y times or x times log of x upon y. Who can tell me whether this is a convex function or not? This we have already done in some ways. Of so this is actually a perspective of this. Okay, so remember that perspective means y times f of x upon y. So the outside y actually gets cancelled. Okay, so what is the perspective of this function? It is y times f of x upon y, which is x upon y times log of x upon y. Okay, and if this function is convex, then the perspective is also convex. Okay, now this is really hard for any rule based check. Okay, because you have to check whether it is a perspective of some other convex function, which is just not possible. Okay, so things are quite difficult. Okay, in this regard. Okay, what about this function? One more example. Okay. Y e to the power x upon y. This is perspective with respect to e to the power x. Okay, so this must be convex. All right. So what some solvers actually do is to some people have actually gone through hundreds and possibly even thousands of models of Minello examples that exist in various repositories, and tried to check what kind of functions do we see in these models, okay, coming from various practical applications. And some of these rules are actually these ad hoc rules are directly implemented in solvers, that whenever you see a term like this, it is a convex function, okay. Similarly, if you see a term like this, then just straight away, without doing any tests, just mark it as convex, okay. So, a list of such rules, one such list of such rules is available in this paper by Khajavirad and Sahinitis, who implemented many of these rules in Baron, okay, 2018, and showed that once you know that many of these functions are convex, a lot of these global optimization problems can be speeded up really fast, okay, because then you don't decompose them into small factorable functions, because if you look, if you have such a function, then you have to first introduce a new variable saying that w is equal to log of x, and then another w2 is equal to w1 into x, okay, and then relax them separately, which is very weak, okay. But if you know it is convex, you don't need to relax, you just take linearization inequalities, okay. So that makes one big difference for these techniques, all right. There are also rules for products. So for example, one such rule is this: if you have a product of many terms where we have variables x1, x2 each raised to a different power, and we know that the domain of x, okay, is such that it is bounded away from 0. So it is strictly positive always, and ai are all less than 0, okay, then this function is convex. Okay, so for example, 1 upon x1, x2 square, I think. Okay, of course, the domain is important. Okay, so this function is not convex everywhere, but if you say that xi is, for example, between 1 and 10, okay, then this is a convex function. Okay. Similarly, some rules for exponential type of functions. So if f of x is equal to product of ai to the power of xi, okay, where again each of the xi's are strictly greater than 0, and ai's are negative, okay, that looks strange, okay, so ai's are negative, then again this function is convex, okay. We already talked about these type of norms. A similar form which is convex usually is, which is this: f is equal to a naught plus summation ai xi to the power p raised to the power q. Okay, if we look at this function, so in this example, q is half p is 2, okay. So this function is, yeah, yeah. Then it doesn't even make sense, okay. So I will double check, okay. So maybe this is positive, okay. So, uh, so, so, so wait here, okay. So I'll just confirm in the end, okay. I'll just double check and then tell you, okay. So, so for this type of a function, if p is greater than 1, q is greater than less than 1, and p times q is greater than 1. So this is this type of a function. Then f is convex. Okay, and same function again, but if p is less than 0 and 0 less than q less than 1, then also f is convex. Okay. So an example of this is, for example, 1 upon 1, 6. Okay. So, so in both these AIs must be strictly positive, and here also AI must be strictly positive. Okay, so this is an example. Okay, and of course X must be, more than 1 or something. Okay, more than 0 at least. Okay, so many such rules you can try. The other side is also quite interesting. Suppose you want to prove that, or you have tried your bag of tricks. Okay, so you have tried to fit your function into any of these forms or many others that may exist, and you are unable to show that function is convex. Then you can still, you are still in some sort of a dilemma. Can I still try, convexity based approaches, or you can try to write a proof that it is really non-convex. Okay, and one way to do it is to take an f and find its pick a point x and compute its Hessian and check whether it is not positive semi-definite. Then it is a proof that it is not convex. Okay, so that you have to try at many different x's. Okay, a one trick which was proposed by Bob Fuhrer and Dominic Urban and few others in 2009. There is a tool called Dr. Ample. Okay, which looks at ample models and tries to glean as much information about the type of model as possible. Okay, so it checks for convexity, it checks whether functions are increasing or not decreasing, and so on and so forth. Okay, so this is by Fuhrer, Bob Fuhrer, who also wrote ample, and Dominic Urban, 2009. Okay, so so a small shortcut they propose for checking for non-convexity is, rather than trying to find positive semi-definiteness of the Hessian matrix, what they say is, so given some f, okay, you try to solve this optimization problem. Okay, so you try to solve a trust region problem of the following form. Okay, G transpose D. Okay, so this is a minimization problem in D, which is D is the direction. Okay, so remember that things are not semi-positive, semi-definite when we can find directions of negative curvature. Okay, so instead of trying to find eigenvalues or some such thing, we can directly try to find some directions where the curvature is negative. Okay, so what they propose is solving this problem, D transpose. Okay, and put some bounds on D. Okay, so for example, you can put an ellipsoid constraint or a truss region or a ball constraint on the set of directions. Okay, so D is the variable, so you don't have you are solving for D. The other parameters are this, which is the Hessian of the function at a given point, and G is some random vector. Okay, that you can choose. Okay, and this is your some radius, which again you can choose. Okay, some small positive number, and you can try this for many different x hats and try to solve this problem. So it turns out that solving this problem sometimes is much faster than checking for positive semi-definiteness. Okay, because this is a standard truss region problem, for which Sven can do another GIAN course maybe next year and tell us about all the very nice methods. You know, there are fat books written on solving just this problem, okay, truss region problems, and there are a lot of you know, tricks to solve this fast. Okay, and you can try many different x hat values and try to prove this. Okay, so that, you know, if you are able to find such an x hat, then that gives you some solace that I am able to prove that it is not convex. Okay, and then you stop searching through your bag of tricks. Okay, whether you know, my function fits convexity or not. Okay, all right. Last thing before we stop is you know, your function may actually be composed of several such functions. Okay, so for example, your function may be a sum of a function of this type plus a function of, you know, this type. So you don't, you know, apply these bag of rules directly to the function, but to the computational graph. Okay, so so if you have your expression graph, you know, if you have some graph, you can start from below and say, you know, in the beginning at the leaf nodes, you might have some constants or some variables. So these are either you say that these are affine functions or linear functions or just variables, and then you start you know, propagating up and checking whether you know, the functions are still convex or not. Okay, so for example, if I do x1 plus x2, so that means I can say that the function here, if I look at the subgraph below this node, I can say that it is an affine function, number one, and I can also say that it is a non-decreasing function in both variables. Okay, so it is non-decreasing. So remember that these two properties are important to prove convexity. Okay, and other such markers which I can propagate and check whether it is really convex or not. Okay, so writing this code or you know, checking for these rules is pretty interesting and you know, requires some effort in keeping track of what we are doing. There are many other results related to you know, this convexity checking. So for example, if you don't say that any arbitrary functions, but you say I am going to focus only on certain types of functions. So for example, cubic functions, are they convex? Not really. Whenever you have some cube, it will be some non-convex thing. Okay. What about functions of fourth order? They may be convex, may not be convex. Okay. Our first example. Okay. So an interesting question is, can you check whether a given polynomial is convex or not? Forget other functions which have exponents or cosines or some such thing. Okay. So there is a result which says that given a polynomial, whether it is convex or not, that problem is NP hard. Okay, so there are no short algorithms or fast algorithms which will tell you whether a given polynomial of kth order in multiple variables is actually convex or not. Okay, so things become complicated quite fast. All right, and there's a lot of, or there is at least some work going on to tackle this beast as well. Okay, and it's a very important component of global optimization. Okay, so many solvers have this fallback option that the user can say that you can assume everything is convex. Okay, so sometimes solvers will fail to check or fail to say that this is a convex model, but if the user just says that you assume everything is convex, then we just sit back, relax, and use linearization type of ideas. Okay, so that really helps. So sometimes help from humans is very important. All right, thanks a lot.